In this lesson, we're going to talk about angular momentum. Angular momentum is somewhat similar to linear momentum. Remember, linear momentum is a quantity of motion that's found by taking mass times velocity using the formula P equals mv. That's linear or translational momentum. Angular momentum is somewhat similar, except instead of a linear velocity, we're talking about a rotational velocity or an angular velocity. The symbol we use for angular momentum is an L. And we can find the angular momentum by taking r perpendicular times the linear momentum. Or in other words, r perpendicular times mv, which is the same as saying r mv sine of theta, or r cross mv, r cross p. That's how you find the angular momentum for an object that has a linear velocity, v. So we can also find the that is an equals there. We can also find the angular momentum of a rotating object by taking I times omega. So we have these two different ways to find the angular momentum of an object, depending on whether it's a linear moving object or an object that's rotating. In order for this linear moving object to have angular momentum, notice it has an r perpendicular. Remember, that's the perpendicular distance from the axis of rotation to the line of action, or in this case, to the line of velocity. Let me just give you an example. Suppose I have a bullet, a 3-gram bullet, so 0.003 kilogram bullet, traveling at 300 meters per second. And there's a wheel out here, a cylinder, uniform solid cylinder. Okay. Yeah, nice try. Anyway, uniform solid cylinder. So the line of this velocity, if I were to trace out this line of velocity, it's going to hit it right on the edge of that cylinder. Okay. So because this line of velocity does not line up with the axis of rotation, there is, in fact, an r perpendicular. Notice it's this distance here. This would be r perpendicular. The perpendicular distance from the axis of rotation to this line of action, in this case, this line of velocity. That's my r perpendicular. So this bullet does have angular momentum with respect to this wheel. Now, if the bullet's line of velocity were lined up directly with the axis of rotation, then there would be no angular momentum. Okay? So that's what it means by a linear moving object having angular momentum. It is only defined in terms of an axis of rotation for which the line of velocity does not pass through. Now, a couple of other interesting things. With linear momentum, the net force was equal to the rate of change of momentum, so delta p over delta t, or dp dt, which meant that if the net force is 0, then momentum is conserved. We have conservation of momentum that way. Similarly, just as with linear forces, if we look at torques, the rotational counterpart of force, the net torque is equal to the time rate of change of angular momentum, or in other words, dl dt, or delta L over delta t, and therefore, if the net external torque is 0, then angular momentum is conserved. So we have conservation of angular momentum. Let's look back at this example here. Here I've got a bullet. Let's suppose this bullet, as it's traveling along, is going to hit and become embedded in the wheel right at the edge here, and that's going to cause the wheel to begin to rotate. Let's say the wheel has a mass of 5 kilograms and a radius of 0.25 meters. Okay. So I'd like to know, what is the angular velocity after the bullet impacts? Well, if I have conservation of angular momentum, that means that the initial angular momentum must equal the final. Initially, all of the angular momentum is in the bullet. Because it's a linear moving object, I'm going to go with the formula r perpendicular mv. So r perpendicular, we'll use a little m for the bullet, and we'll use a big M for the cylinder. And I'll put v naught there, because that's the initial velocity there. Is going to equal the final. Now, finally, the bullet becomes stuck and becomes embedded in the cylinder, in the wheel. So what I have here is I now have a rotating object. So I'm going to use the inertia times omega, I omega. So the inertia is going to be the inertia of the bullet plus the inertia of the wheel, and the inertia of the bullet as a particle is simply mr squared. Plus the inertia of the wheel, being a uniform solid cylinder, axis through the center of mass, is going to be 1/2 mr squared. Notice this is the bullet's mass here, this is the cylinder mass here, and that's going to be, of course, times omega. That's I combined inertia of bullet embedded plus the cylinder times omega. So now at this point I can either solve it symbolically or I can plug in some numbers. So if I plug in some numbers, what I have is 0.25 times 0.003 times 300 equals 0.003 times 0.25 squared plus 1/2 times 5 times 0.25, that's my r, squared, and then that thing is times omega. So let's pull out a calculator and do some quick calculations here. Alright, so on the left side, 0.25 times 0.003 times 300, I get 0.225. On the right side, 0.003 times 0.25 squared plus 0.5 times 5 times 0.25 squared, I get 0.1564375, and that's times omega then. Then I divide both sides over, I end up with 1.438274071, or let's just round that to three significant figures, 1.44. That's going to be radians per second equals my omega. So that is the angular velocity of the wheel after the bullet has struck and become embedded in the wheel. Another application of angular momentum are figure skaters. For example, a figure skater, if we look at conservation of angular momentum, L initial equals L final. So that's going to be I naught omega naught equals I final omega final. So a figure skater, for example, can start into a spin with arms and legs stretched out, giving a large I value, large inertia, and whatever omega they have. They then bring their arms in, which decreases the inertia. And by decreasing the inertia, you automatically increase the final omega. So that's how figure skating works. Is they start the spin with a large inertia, the arms outstretched, and then as they bring the arms in, they're decreasing the inertia, which causes the angular velocity to increase. Another example of conservation of angular momentum are satellites in elliptical orbits. For example, here I've got a planet, I got a satellite here, and it's in an elliptical orbit. Let's call this position A and this position B. So this we'll call RA, and this we'll call RB. So for example, the only force acting on the satellite is the force of gravity. And the force of gravity does not produce any torque, and therefore angular momentum is conserved. So the angular momentum at position A is equal to the angular momentum at position B, which is to say RA times MVA, that's just R perpendicular MV for position A, is equal to RB MVB, just the angular momentum at position B. Notice the mass of the satellite will cancel out, leaving you just RAVA equals RBVB. So from here you can do things like, you can get the ratio of the radii equals this ratio of the speeds and things like that, depending on what information you have and what you're looking for. But satellite problems are a good application of conservation of angular momentum, especially if the orbit is elliptical. I hope this has helped you understand a little bit better about angular momentum.